All right, one more time. We're going to do our introduction to synthesis now. In a synthesis problem, you are given a compound, and you're asked to make that compound starting with either something I give you, or in this case, with anything you want, any appropriate alkene. Let's go ahead and start with our first one here. What you do in a synthesis problem is you talk to yourself a lot. Quietly. You look at this and say, what kind of a molecule is it? What kind of compound is it? And then, how many ways do I know to make that particular type of compound? So we look at this and we say, it's an alkyl halide. Okay, I can do that. I know that alkyl halides can either be Markovnikov regiochemistry or anti-Markovnikov. So we look at this and say, the bromine is not attached to the center in the molecule that would be the most stable carbocation. Therefore, this is an anti-Markovnikov alkyl halide. So that's the answer to the first question. What is this molecule? It's an anti-Markovnikov alkyl bromide. The second question you ask is, okay, how many ways do I know to make anti-Markovnikov alkyl bromides? One. Just one. That's the addition of HBr to an alkene with peroxide present. So what alkene would you need? Well, we would need a double bond here somewhere. This one will work. Our reaction conditions. We simply need to show HBr peroxide. Now we could not have had our double bond out here, could we? Because if we did, the bromine would go to this carbon, not this one. So this is the only simple alkene that would give rise to this bond. This is the Markovnikov carbon. Bromine will go to the anti-Markovnikov position. Now that's simple, isn't it? If we had tried to use this alkene here, and we'd added HBr, not HBr peroxide, just HBr, you could say to yourself, okay, hydrogen's going to go here, bromine will go here. Will that work? No. Not at all. Why is that?
It's not anti-Markovnikov.
Because this is stepwise. We're going to form a carbocation, and it's going to rearrange. It would look something like this. If we took this guy and we added HBr, we would put proton here, carbocation here, right? But before bromide could add to the carbocation, we would get a hydride transfer. We would then add to the tertiary carbocation and get the wrong product. So the only one that works is the other alkene with hydroboration oxidation. All right, look at this and answer my question. What type of compound is it? How do I know to make that type of compound? What alkene would I need to use to do it? Well, what type of compound is it? What's our functional group here? It's a halohydrin, isn't it? OH on one carbon, halogen on the other. Halohydrin. The hydroxyl group is attached to the tertiary carbon here. That would be our Markovnikov carbon. And that's good, because the only way we know to do this is to simply add HOBr to an alkene. Remember, when you add HOBr to an alkene, the OH group goes to the most stable carbocation. So, draw the structure of the alkene that you would need and put down the reaction conditions that you need to run the reaction. These two carbons, here and here, need to be the carbons of the alkene, don't they? And our reaction conditions to make a halohydrin is simply going to be HOBr. These two carbons were the alkene carbons. We added bromine here, OH here. Our next compound. Do the game here. Look at it and say, what type of compound is it? How do I know to make that type of compound? What alkene would I need? What compound would I need in order to do that? Well, very simply, this is a trans 1,2-dibromide, isn't it? Bromines are trans. How do you know to make trans 1,2-dibromides? You only know one way, and that's to take an alkene and add bromine. So quickly jot down the structure of the alkene that you need to make this. In the alkene, these were our sp² carbons, weren't they? We know that because that's where the bromines went. Therefore, all you have to do is draw this guy and show bromine as your reaction conditions. Our double bond is right here, and this is just an ethyl group sticking out. All right, look at this guy. ask our magic questions. What type of compound is it? Well, it's an alkyl bromide, right? What's our regiochemistry? Is the bromine attached to the most stable carbocation center?
Yes.
Bromine is attached to a tertiary carbon. So yeah. So it's an alkyl halide. It is a Markovnikov alkyl halide. How many ways do I know to make Markovnikov alkyl halides? See how simple this gets? Because you only know one way. You take an alkene and you add HBr. What alkene? Go ahead and draw an alkene. That'll work. Carbon skeleton's the same. You just need a double bond in there, don't you? Carbon skeleton's going to have 1, 2, 3 as your parent, a methyl group as a branch, and again our reaction conditions, just HBr. That will work. Where's our Markovnikov carbon? It's here. So bromine goes to this carbon. This guy picks up the hydrogen. Is that the only correct answer?
Yes.
How about this reaction? Where is the Markovnikov carbon? It's here. Bromine goes to this carbon, hydrogen goes here. That works too. Is that the only one? We can do this again, can't we? What if we put our double bond all the way out here on the tail?
If you say 1, 2 hydrogen, it will work.
Our carbocation would form here, but we would get a hydride transfer. Carbocation would move to here, and we'd make this compound. So on an exam, if I gave you this, you could draw any of these guys and get full credit. Isn't that fun? As you get into doing multi-step synthesis, which is what you'll do next semester, you'll have 2 or 3 steps in a reaction. You'll be amazed at the pathways that you can come up with to get from here to here. Organic chemistry is so versatile that it just really relies on your imagination to come up with novel pathways. Now, mind you, it makes grading exams really tough because every question can have multiple answers. But this is really fun, isn't it? Another way that these questions appear on exams is in this format. Here I give you an assortment of compounds, and I give you a target, and I say, pick one of these guys and make this compound. Well, our logic is exactly the same here, isn't it? We look at this and say, what kind of compound is it? It's an alkyl halide. What's my regiochemistry? Is this Markovnikov or not? It's anti, right? What alkene would give me this compound There's only one way I know to make these, that's HBr peroxide. So which of these compounds could I react with HBr peroxide and get this thing? So, it's an alkyl halide. It's an anti-Markovnikov alkyl halide. And we need to add the bromine to the end of our chain. So we look at our compounds here. The end of our chains kind of looks like these three, right? So which of these three could we react with HBr in the presence of peroxide to make this stuff?
First one.
Well, this is actually really simple because only one of these terminals has a double bond, doesn't it? So it's got to be this guy. What do you put down for reaction conditions? We are simply going to use the only reaction we know to give anti-Markovnikov alkyl halide is HBr peroxide. Any questions? Well, let's do it again. Here we have an alcohol. Ask yourself the magic questions and pick a compound and write down reaction conditions. All right, step one, what kind of compound is it? Well, it's an alcohol. Not only that, but it's a tertiary alcohol. Because it's a tertiary alcohol, that means that our regiochemistry is Markovnikov. That means that the OH is bonded to the carbon that would give us the most stable carbocation. How many ways do I know to make Markovnikov alcohols? Only one. Acid catalyzed addition of water. All right, so which of these? It's added to the tertiary carbon. We look at our three possibilities. There's our tertiary carbons up there. We need to do acid catalyzed addition of water and put a hydroxyl group here, here, or here. Which ones would work?
2 and 3.
Because this is a stepwise reaction and we can get rearrangement. All of them work, don't they? So once again, if you simply wrote down any of these guys, strong acid and water, you could even put just H plus H2O, you would make this alcohol. These two would add directly. This, we would get a rearrangement to get the alcohol. We could do this in a more civilized way. Remember, we can also make Markovnikov alcohols with mercuric acetate followed by sodium borohydride. In that case, we don't get rearrangement, so only these two would work. Again, on the exam, you could have done any of these things and get full credit. Let's do another one. You know the drill. What type of compound is it? What's my regiochemistry? How many ways do I know to make it? What alkene would I need? And what are my conditions? Synthetic logic is the thing that makes organic chemistry unique because you get to think backwards. All right, what kind of compound is it? Well, it's an alkyl halide. Is the bromine attached to the most stable carbocation? No. No, it's attached to a secondary carbon. We got a tertiary. Therefore, this is anti-Markovnikov. How do I make that? HBr peroxide and an alkene. All right, look at our possibilities. We're attached here to the secondary carbon. Secondary carbon up here is going to be this guy, or this guy. So pick a starting material. This guy's out because there's no double bond there, right? So it's either this one or this one. If we add this one, which is our Markovnikov carbon, this guy, the secondary. This guy is our secondary. Therefore, those two don't work, just this one. And our reaction conditions, all you have to do is remember HBr peroxide.
So there's no hydration between
Nope.
anti-Markovnikov.
No rearrangements.
So that's it.
Next one. What type of compound is it? It's an alcohol. What's my regiochemistry? Markovnikov or not? Markovnikov carbon would be the tertiary. This is a not. Primary alcohol. Anti-Markovnikov. How many ways do I know to make anti-Markovnikov alcohols? One. Hydroboration, oxidation. All right, we're attached here out to one of the arms next to the tertiary center. Up here, that would correspond to this, or this. Only one of these possibilities has a double bond, doesn't it? So that makes it simple. We must use this as our starting material. And our reaction conditions, we simply remember hydroboration, oxidation, anti-Markovnikov alcohol. One last one in this set. We look at this and say, what type of compound is it? It is a alkyl halide. What's my regiochemistry? Markovnikov or not? Is it attached to the most stable carbocation center? Absolutely. How many ways do I know to make Markovnikov alkyl bromides? One. Take an alkene and add HBr. That's it. We're adding to our tertiary center. So that's going to be one of these guys. These two have double bonds already. Either of those will work. This is an ionic reaction. So this one, if we added here, would rearrange to this center too. Because it's ionic, all of these work. So all you have to do for conditions is show HBr. All right, this type of question obviously just deals with reactions of alkenes. But we know so much more than that, don't we? Therefore, we can build upon this and ask this question instead. Here we have an entire assortment of starting materials. And we have a target. What you do is you simply look at all these guys, look at what you're trying to make, and ask, what is it? How can I make it? What do I need? And you pick it out. So exactly the same game here. What is this? It's a 1,2 diol, isn't it? The OH groups are on the same side of the molecule. So this is a cis 1,2 diol. Now I actually know two ways to make cis 1,2 diols, permanganate and base or osmium tetroxide. But they're exactly the same reaction, so either one would work. The next thing we want to ask, because this is a cis addition, is where are my methyl groups? Well, the methyl groups here are trans to each other, aren't they? They're on opposite sides of our molecule. Therefore, this is a trans molecule. This used to be our alkene carbon, and we made a 1,2 diol. All right, our parent here must have 1, 2, 3, 4 carbons, right? So we look up top. Look for a 4-carbon backbone. We see basically 3 compounds. Now we know we want to make an alkene, or a cis 1,2 diol, so we need an alkene. So we can rule out the alkyl bromide right away. Do we want this guy where the methyls are trans, or this one where the methyls are cis? Well, here, our methyls are trans, aren't they? They're not going to move. Therefore, we want the trans alkene trans 2-butene is what you're shooting for. Now all you have to do is write down the reaction conditions. Remember, to make a 1,2 diol out of an alkene, we simply need permanganate in base. Permanganate in acid, remember, splits it. Permanganate in base makes the 1,2 diol. Cis stereochemistry. Any questions? Well, then let's do it again. Ask yourself the questions quickly. What is it? How do we know to make it? What's our backbone? Pick a compound. Think up your reaction conditions. Well, what is it? It's an aldehyde, right? Turns out that you know 2 ways to make aldehydes. We can make that from an alkene with ozonolysis, or we can hydrate an alkyne anti-Markovnikov. So now you know 2 ways. So you're either looking for an alkene that you can split, or for an alkyne that you can hydrate anti-Markovnikov. You know it's anti-Markovnikov because the oxygen is not on the most stable carbocation. Well, as we look around, we have a 3-carbon backbone here. My gosh, there's only one 3-carbon backbone, isn't there? That makes it simple. So we're obviously going to use this alkyne. So remember back to earlier today, how do we hydrate this anti-Markovnikov? Same way we do anti-Markovnikov alcohol on an alkene, and that's hydroboration, oxidation. OH goes to the anti-Markovnikov carbon, hydrogens go to this guy. Quite often I will put a question sort of like this in a different context on an exam, where I will give you an alkyne. I will ask you to show the enol intermediate and then clearly show how that converts to the carbonyl. So we have a slide like that. Make sure that you understand that, because again, that's a standard test question. Let's do another one. I can do this all day. All right, what kind of compound is it? It's an alkene. How many ways do we know to make alkenes? How many? 1. Elimination reaction. Just 1. So, we need something with a leaving group here, where we can do either an E1 or an E2 elimination. It's an alkene. We're going to make this by an elimination reaction. We're dealing with a cyclopentane. And we need a leaving group on one of these carbons. So look at our collection here. We're looking for cyclopentanes. We have 4. In this guy, the leaving group is out here. It's the wrong place. This guy doesn't have a leaving group at all. It's an alkene. Forget that one. This guy has a leaving group on one of the alkene carbons. And this one has a hydroxyl group, which isn't a really good leaving group. Therefore, what we're going to use is this guy. Now, what do we put for our reaction conditions? Remember, to do an elimination reaction, what do we need? If I wanted this to be a nice clean elimination, an SN2, what's the magic thing I write for SN2? Terbutoxide. Big, ugly base. Not going to do substitution. It's just going to act as a base, yank off the hydrogen, and give us the alkene. Big, ugly base. Can't do substitution. Therefore, you only get elimination. Everyone write down big, ugly base? I hope so. All right, this is the carboxylic acid, isn't it? How many ways do we know to make carboxylic acids? 2 ways, actually. We can split an alkene to make carboxylic acids, or we can split an alkyne to make carboxylic acids. It's a carboxylic acid. We're going to make this by oxidation of an alkene or an alkyne with permanganate. This is acidic permanganate, remember. So we're looking for a 2-methylbutane backbone. So 1, 2, 3, 4 carbons is a butane with a methyl group out here. This carbon was either part of a double bond or a triple bond. We only have one possibility, and it's this guy. If we take this and simply split our triple bond, we would make a carboxylic acid out of each carbon. What's our reaction condition? Permanganate and acid. Oh, it's an ether. How many ways do we know to make ethers? 1, by an SN2 reaction, right? So we need an alkoxide, and we need a leaving group here. We're going to make this ether using an SN2 reaction with an alkyl halide and an alkoxide. Now remember, we could split on either side here. Split here or split here. So we could actually look for 2 different alkoxides. We have a cyclopentane backbone. So again, let's look at our cyclopentane list. We need something with either an OH here, we don't have it, or a leaving group here. And we do right there. Now, how do you make this into an ether? All you have to do is take this and react it with an alkoxide. The alkoxide is simply a methyl group and an oxygen, and that's all you'd have to show.
So, in fact, I'm not sure if register this course.
Slightly different set of reactions. Actually, to be honest, that means this is a different exam, doesn't it? So we just took one exam. We're taking another exam. What type of compound is it? It's an alcohol. What flavor of alcohol? I don't mean spearmint. It's tertiary. That means the regiochemistry is Markovnikov. We know we can make Markovnikov alcohols in a rather brutal reaction with acid and water, or a more selective reaction with mercury and water. Acid catalyzed hydration of an alkene. So, we look at our list. We're looking for our cyclohexanes. These are these two compounds. So what you have to do is pick which one of these you want to make this guy. Now, how are we going to make this? Acid catalyzed hydration, carbocation intermediate. So it's going to rearrange, isn't it? We could actually use this one and it'll rearrange to that carbocation. Let's just do this one because it's cleaner. And all you have to do for conditions is show acid and water. If you were to put this one on the exam, you would get full credit.
How many of those are total, Dr. Young, the reaction mechanisms? How many are in total? 16, you said?
Oh, I think so, yeah. Something like that.
Come on, index cards.
You gotta write really small to get them on your card. So, I mean, that's why I let you take the card. But reading the card on an exam is just about as tough as just remembering it. Nonetheless. All right, let's do this one more time, two more times. Again, we have an alcohol. It's a secondary alcohol. That means it is anti-Markovnikov, isn't it? Now we've done this a lot. How do we know to make anti-Markovnikov alcohols? Hydroboration, oxidation. Right? See how simple this is. So we look, again, we're looking at the same two cyclohexanes. These guys. Which one do you want to use? With this guy, the tertiary carbon is our Markovnikov carbon, and the hydroxyl group would go here on the secondary center, right? On this one, both of these are secondary, right? So it could go to either one. Actually, it would be most likely to go to the wrong one down here, because the methyl group's in the way there. So we want to use this as our starting material. What are our reaction conditions? Anti-Markovnikov, high deboration oxidation. Whoops. How did that happen? That's not supposed to be there. Hang on. There it is. I forgot to delete that on the slide. Remember, if you would have put this one, the hydroxyl group would have gone either to this place where you want it, or this place that you don't. And it's actually most likely to go here because the methyl group would be in the way. So this would get you half credit. And our last one. Something to look forward to. How about if I just stay quiet for a second?
No.
Everybody ask your own questions. Pick a starting material. Do your reaction conditions. What type of compound is it? It's an alkyl bromide. What's the regiochemistry? The most stable carbocation is our benzyl position. Therefore, this is anti-Markovnikov. We know that we're going to use HBr peroxide to make this. And we know we're looking for a starting material with a benzene ring. There are only two. Now this is even simpler than that, isn't it? Because we need two carbons attached to the benzyl position, right? Here we only have one. Here we have two. It must be this as our starting material. And for our reaction conditions, we simply need to put HBr peroxide. This is organic synthesis. This is what it's all about. This is why you had to learn all those reactions. This is the fun part of organic. Next Tuesday, we will do Chapter 10. Chapter 10 is even simpler, full of lots of pretty color pictures. All we're going to do is talk about radicals and alkyl halides. Very simple chapter. And then we get to have Thanksgiving. I will send everyone an email when I get the final details on the lab. Well,